In the first objective of Term 2, we shall be looking at defining a force, what it is, introducing free body force diagrams, and naming the type and direction of forces acting on bodies. A force is defined as a push or a pull of one body on another. The SI unit that all forces are measured in is the Newton, symbol capital N. Forces are vector quantities. They are fully defined by having size and direction. They're usually represented by an arrow. The length of the arrow is an indication of its size. The longer the arrow, the greater the size of the force. And the direction of the arrow signifies the direction of the force. So, for example, the force could be acting in the opposite direction. A free body diagram is a diagram showing the body on its own, free from its surroundings, and the forces that are acting on it. If we wanted to represent a car, for example, we would represent it as either a box or a dot. This could represent our diagram of the car. This could represent our diagram of a physics book, or it could represent our diagram of a person. The diagram shows the body on its own, but to make it a free body force diagram, we need to show the forces that are acting on it. Now we shall discuss the forces that are acting on the books. The first force we shall consider is the gravitational force. We write this as F gravitational. Gravitational force is also called the weight of the body. The weight of the body is the pull of the earth on the body, and it acts on all bodies on the surface of the earth. We represent this as a force with an arrow starting from the body, pointing vertically downwards, because weight always points vertically downwards. The weight of the gravitational force is found by the following equation. Gravitational force equals mass times g. G is, of course, known as the acceleration due to gravity, or the gravitational field strength, and takes a value of 10 newtons per meter. So the gravitational force for a mass of 5 kilograms is known to be 50 newtons. So we can represent this with an arrow pointing downwards and a label to the size of the force, 50 newtons. The weight of the body acts all the time, wherever it is, even if the body is in the air or at rest on a table. If our body is in contact with another body, for example, if it's at rest on a table, then there is another type of force, which is called a normal reaction force. The second type of force is the normal force. The normal force is the force that acts only if the body is in contact with another body, and the force that acts is always perpendicularly away from the surface of contact. In this case, since the book is in contact with a table, then perpendicularly away from the table, the normal force will be acting vertically upwards. The vertical is the perpendicular to the table. So we show this with an upward pointing arrow and a label, force normal. Now, if these two were the only forces that were acting on the body will remain stationary. In order for it to move, let's say to the right, we have to apply a force on it. And so that is a pushing force. Or, in fact, if we acted it this way, it will be a pulling force. If such a force were acting on a body, we could label it with an arrow to the right, F pull, or pulling force, or F push, if we were acting from behind, a push force. Or we normally just call it an F applied. It's an applied force. Whether it's a push or a pull, it's called an applied So we normally just label it with an arrow and say that it's F applied independently of whether it was a pull or a push. So an applied force is a force that is acted on a body, and it's simply labeled F applied. So it has an arrow to show the direction and the size. Now, if the body was set in motion, either by the action of an applied force or whichever way, it would be in contact with another body. In that case, there will be another force, a force of friction. Friction force acts when the bodies are in contact with each other, and it will act in the opposite direction to the motion. So if this book were moving to the right, it will then have a friction force which would be acting to oppose its motion, or in the opposite direction to its motion, acting to the left. Note that I made the arrow here smaller, just simply to say that if it's a smaller arrow, it means that it's a smaller force than the applied force. And we can label the force of friction. So now we have seen the four most common forces that are acting on the bodies. The gravitational force, which is the weight, acts on all bodies. The normal force acts only if the body is in contact with another, and it acts perpendicular to the surface. The applied force is if we apply a force on a body, and the friction force, which acts only if the bodies are sliding over each other. So the diagram here would in fact be a free body diagram. It's a diagram showing the body and the forces that are acting on the body by the surroundings. The earth pulls the body downwards. The table pushes the body upwards. An applied force causes the body to move to the right. And because it's sliding over a surface, a frictional force will want to cause it to slow down or to move to the left, to oppose its motion, in other words. So in summary, we have defined the force as a push or a pull of one body on another. We have looked at what a free body force diagram is, and we have named four common forces that are acting on bodies.